The topic of this video is ANOVA, mean squares and the common population variance. In an effort to counteract student cheating, the professor of a large class created 4 versions of a midterm exam, distributing the 4 versions among 348 students in the class, so that each version was given to 87 students. After the exam, the professor computed the following information about the scores. The exam was worth 200 points. The table provided to us shows the version of the test that each group received, the sample size of the group, sample mean of the scores on that exam, and sample variance of the scores. Group that received version A had a sample size of 87, sample mean of 155.7, and sample variance of 370.4. Group that received version B was of sample size 87, had sample mean of 156.9 and sample variance of 433.0. Group with version C was of sample size 87, had sample mean of 148.1 and sample variance of 376.1. Finally, the last group had version D, was of sample size 87, sample mean 153.1 and sample variance of 386.7. The professor is willing to assume that the populations of scores from which the above samples were drawn are approximately normally distributed, and that each has the same mean and the same variance. We have 2 questions to answer. The first question: give an estimate of this common population variance based on the variance of the sample means given. The second question: give an estimate of this common population variance by pooling the sample variances given. Carry your intermediate computations to at least 3 decimal places and round your responses to at least 1 decimal place. Let's answer the first question. We are asked to give an estimate of the common population variance based on the variance of the sample means given. It means that we are going to use the 3rd column of the table that provides samples for each group of students. Please notice that I highlighted the statement that we can assume the populations of scores are approximately normally distributed, and therefore the samples drawn from those populations are approximately normally distributed. Because the populations are approximately normally distributed, we can apply the central limit theorem, which states that the variance of the sample distribution will be equal to the population variance divided by the sample size. You may remember this formula or a version of this formula, probably in a slightly different format, just to remind you that you have seen the following, that standard deviation for the sampling distribution is equal to population standard deviation divided by square root of n. This formula was much more commonly used in the topics we have learned in this course. However, please note, if I take both sides of this equation and square, I will get variance of the sampling distribution of x bar, which is equal to the population variance because now sigma is squared, and it is divided by the sample size n without a square root because square root is removed by applying this second power. That's how I got this expression. We are going to find the answer to this question using this equation. My task now is to get information to put into this formula. Well, I know sample size was 87. the variance sigma squared is exactly what I'm looking for. I'm trying to estimate this quantity. Can I get something that can be placed here instead of the variance of the sampling distribution of x bar? Well, I think I can. We're going to do the following. We're going to estimate this number by computing the sample variance using TI-84, and we will use the sample means provided to us. How do I know I can do this? Well, that's what my directions are saying. My directions are saying to make this estimate based on the variance of the sample means given. So I'm going to use this column of 155.7, 156.9, 148.1, and 153.1 as the sample means. The very first thing I need to do is to enter my sample means into the lists. I already did this on my calculator. You can go to Stat, Edit, and just enter your data. There are only 4 numbers. Enter them into one of the lists. I entered it into list 1. Now I use one variable stats, apply it to the first list, and it will produce a lot of useful information about those numbers, but one number that I really want is this sample standard deviation. To make it easy for me to square this number, press bars, choose option 5 for statistics, and choose the number you want. I want to work with sample standard deviation S. I need to square it, so just tell your calculator to square it, and here it is. This is my sample variance because this is the standard deviation squared. You could have just written out the number like I did here that you saw as a result of one variable stats applied to list 1 and then square it, or as I showed, you could use this little tool in your calculator by pressing bars, statistics, and choose the sample standard deviation S, and then tell your calculator to square that quantity. Now that I've found my estimate for a sample variance, I am ready to find my estimate for the population variance sigma squared. Here is the same equation that I showed you before. I know the sample size is 87. I know that variance of the sampling distribution of x bar is 15.237. We just estimated it. Now I need to solve this equation for population variance sigma squared. To do this, I'm going to use the concept of proportions. If I have 2 fractions equal to each other, and by the way, I can express any number I need as a fraction by just dividing it by 1. Now I have a fraction equal to a fraction. It allows me to apply the concept of cross multiplication. I multiply sigma squared with a number across it diagonally with 1, which gives me just sigma squared. And I also multiply 87 with 15.237 again across. And this principle says that these cross products will be equal to each other. As a result of 87 multiplied by 15.237, I get 1,325.6 rounded to 1 decimal place as requested. Now let's answer the second part of this assignment. Give an estimate of this common population variance by pulling the sample variances given. We are again trying to estimate sigma squared, but now we're using different tools to get that estimate. The word pulling just tells me that I need to combine together all of these sample variances. Well, the best way to find an estimate for population variance using several sample variances is simply finding the average of those numbers. Therefore, I'm adding the 4 quantities, 370.4, 433.0, 376.1, and 386.7, and divide by 4, because I have 4 quantities that I added together, and that gives me approximately 391.6 rounded to 1 decimal place. Let's answer one more question. One way to measure the amount of sleep activeness is to measure the percentage of total sleep that is made up of rapid eye movement, REM sleep. REM sleep, often linked with dreaming, is marked by very high brain activity. In fact, REM periods may be the sleep periods in which the brain is most active. REM sleep takes up a mean of about 25% of the total sleep time, but this varies from sleeper to sleeper. In an experimental study, sleep researchers examined 8 adults who are classified as very active in their daily lives, according to such criteria as amount of exercise and type of occupation. 8 who are classified as moderately active, and 8 who are classified as inactive. The researchers record, for each participant, the percentage of total sleep time over the course of 4 nights that is spent in REM sleep. The summary is as follows. We have 3 groups, and for each group we are provided with sample size, sample mean, and sample variance. The group of very active participants had sample size of 8, sample mean of 23.6, and sample variance of 3.4. Moderately active group had sample size 8, sample mean 22.9, and sample variance 9.5. Finally, the inactive group had sample size 8, sample mean of 25.5, and sample variance of 6.9. The researchers conduct a one-way independent samples ANOVA test to determine if there is a significant difference in the mean percentages of REM sleep times among the 3 groups. We have 2 questions to answer. The first question: what is the value of the mean square for treatments, the between groups mean square, that would be reported in the ANOVA test? Second question: what is the value of the mean square for error, the within groups mean square, that would be reported in the ANOVA test? Carry your intermediate computations to at least 3 decimal places and round your responses to at least 1 decimal place. Let's work with the first question. What is the value of the mean square for treatments, the between groups mean square, that would be reported in the ANOVA test? To answer this question, please remember the following formula. Mean square for treatment, MSTR, is found by multiplying sample size, n, by variance of the sample means. So MSTR is equal to n times sigma squared of x bar. We know that sample size is 8 for each group. To get sigma squared of x bar, you are going to use the same technique I just showed you with the previous example using your TI-84. Please enter your data into one of the lists. Apply one variable statistic to that list to compute the sample standard deviation S, and then square it to get the sample variance. Once you get this result, please multiply it by 8 and round your number to 1 decimal place. 8 times 1.34536 squared is equal to 14.5. Please remember that directions say to use at least 3 decimal places for numbers when you do computations prior to the final result. I went and recorded up to 5 decimal places. 3 would be sufficient, but I went a little higher. If you use the function of TI-84 that I demonstrated to you with the previous example, where TI is just copying the standard deviation from the one variable stats result, then TI-84 does a much more precise job than I'm doing here by rounding to the 5th decimal place. But again, Alex will take a more precise answer as long as it's not less precise. So please do not round to 2 decimal places within the computations, or you will be marked wrong, as your result may be slightly off. The last part of this assignment is asking the following. What is the value of the mean square for error, the within group mean square, that would be reported in the ANOVA test? This particular question can be easily answered by simply finding the mean of the sample variances. Remember that the within groups means I'm working with the error, And mean square for error is actually the mean of the sample variances. So you need to take the sample variances given to us of 3.4, 9.5, and 6.9, add them together, divide by 3 to find the average of these three quantities, which happens to be 6.6, and you found your answer.